Welcome to the last session in this section where we are talking about the DC circuits with dependent sources. We also talked a little about an AC source, but it doesn't matter because the general ideas remain the same. Okay, I suppose by now we are more familiar with the ideas and also the thought that it's easier to do dependent problems, especially because there is dependence, and dependence means that there is a lessening of variables, and so we will be able to do any problem provided we have an understanding as to how to distribute the currents. If current is the main if current is the initiator of the problem, otherwise we will distribute the voltage. In this session we will be seeing that the distribution of voltage is also important. Okay, so they are supposed to be the problems that will be dealt with in this session. Will give you a better idea, perhaps a deeper idea, a deeper understanding, and also help you to do any problems in dependent sources contest. Okay, so let me hope that you realize your own potential and your understanding as we go through the different problems. Okay, so problem number 1 here. It's essentially almost the same as what we have been doing so far. We have the dependent source 3I. It's a voltage source, and I is the current coming out from the 24 volt source as before. Okay, we've seen this, so by now we know that the other sources also need to be taken into consideration, especially because we see I, which means that I is going to be of relevance, and I and 7 ampere, that is the central current source, joined together and must be flowing through the 2 ohm resistor. Okay, so once we have the current flow pattern clear, then we can go for the balancing of voltages via Kirchhoff's voltage law. Okay, so that's exactly what we are doing. Let's see what we require out of the problem. The circuit given below, the current I is very simple in that sense. Okay, so now 24 volt is equal to all the drops, which include 3I. Okay, because you can see that the directions are marked, and so the directions are all marked such that 24 volt, which is a rise from the bottom to top, is now balanced by, again, from the if you look at it from the other direction, you have 3I, you also have 2 into 7 plus I, you also have 3I. Okay, or in other words, 24 volt is equal to 3 plus 2 plus 3, that is 8I, as also 2 into 7, 14. Okay, so now, so it's very simple to solve it. 24 minus 14, that is 10, is equal to 8I. So I is equal to simply 1.25, which is option number B. Okay, so that was a simple problem, but here in the next problem we have a little more to do. Let's see why it is so. Because the circuit is more distributed, unlike in the earlier case. Okay, the first one was just an example, which is a repeat of what we have been doing in session, perhaps both sessions 2 and 3. Okay, so moving on to problem number 2, here we see that we have a current source. Okay, so earlier it was a voltage source, now we have a current source. So please make comparisons and see to it that the ideas are deeply ingrained and entered there. Okay, so we have 0.5 Vx as the current source, which is where the current is pushed upwards. Okay, so that's it. And where does this Vx come from? It comes from the voltage across the 6 ohm resistor. Okay, so immediately we realize that there's a current flow through 6 ohms as given by Vx by 6. So that's all fine. Okay, and we also see that there's a independent voltage 50 volts, so there's only one voltage, so perhaps we may be able to use it in a different manner. And there are so many resistors: 3 ohms, 2 ohms, 6 ohms, and 10 ohms. Okay, so let's see what is required out of us. Thevenin's impedance from terminals AB. Okay, so when you are asked for Thevenin's impedance, we are calling that both Thevenin's voltage as also Norton's current or short circuit current are required, because but the impedance is when you short circuit voltage source, dependent voltage source, you can't short circuit it because you don't know the internal resistance. Okay, it is dependent elsewhere. Okay, similarly, you can't open circuit a current source. That in that sense, you can't find out the Thevenin's impedance in the conventional manner. Okay, so let's start with the Thevenin's voltage. So what do we have here? We see that the voltage across the 10 ohm resistor would be the Thevenin's voltage because AB is open circuit. So that's fine. But then what is the current flowing through 10 ohms? Okay, there are many contributions. Like for instance, let's start from the very beginning. So let's say that I comes out from 50 volt. Okay, that's easier done. So 50 volt, no, please don't say it's 50 volt by 3. Okay, it's just a current I coming out, and at the junction to 6 ohm, another current joins it, which is equal to Vx by 6. Okay, so now Vx by 6 plus I starts to flow through 2 ohms. It arrives at the junction atop the 0.5 Vx current source that also joins it. So in total, we are now having all the three currents, that is I plus Vx by 6 plus 0.5 Vx flowing through the 10 ohm resistor and creating the Thevenin's voltage. Okay, so this is the first thing that we are doing. And now we can balance out different voltages. Like for instance, we know that 50 volt is the same as equal to, there are two, the first loop, that is the smallest loop towards the left. Okay, so we are having 3I as also Vx. So 3I plus Vx. Okay, the directions are perfectly true, or in other words, 50 volt is balanced by Vx plus 3I. Okay, so that's the first portion. Then we are having, let's look at the, okay, of course we can't take the current source, so let's take the overall let's take the next loop, that is starting from Vx. Okay, so Vx is now balanced by, Vx is the voltage across the 6 ohm, is now balanced by the voltage across the Thevenin's voltage as also the voltage across 2 ohms. Okay, so now that's equal to, we are having 2 into I plus 2 into Vx by 6, okay, plus 10 into I, okay, or 10 plus 2, that is 12I, and then we are also having 10 into Vx by 6, okay, so that is, okay, so I suppose 2 Vx by 6, 10 Vx by 6, that is 12 Vx by 6, or we are having 2 Vx, and then it's also 0.5, we also have 0. Okay, of course, there's a multiplication. Yeah, 0.5 multiplied by 10. That's again 5 Vx. So in total, that's 7 Vx. So 7 Vx plus 12y is equal to Vx. So now we have two equations and two unknowns. So you can get a relationship between the two. That is Vx is equal to minus 2i. Okay, and you can also solve for them. And so we see that I is equal to 50 and Vx is equal to minus 100. There are two equations. You can solve them together. So you can solve them like simultaneous equations, and you can see that I is equal to 50 and Vx is equal to minus 100. And so if you substitute for 10 into I plus Vx plus by 6 plus 0.5 Vx, okay, where Vx is equal to minus 100 and I is equal to 50, we get Vth as equal to 100 by 6. Okay, so this is only one phase, okay, and that's why it's all written in red for your subsequent understanding. But now when we go to the Thevenin's current, we have to short terminals AB and start all over again. Okay, so now when we short out terminal AB, that gives you what is called as IN. So now what are the different contributions to IN? One is of course the 0.5 Vx, which chooses no other path other than the short circuit. So we have one contribution coming from the current source, which is equal to 0.5 Vx towards IN because it's a short circuit current. Okay, now we also have a current contribution coming from the 50 volt source. Okay, so there are two sources feeding the short circuit. Okay, so 50 volt source, how do you find the current that is flowing through flowing into the short circuit? Okay, so we see that there's a short circuit at the end, or 10 ohms does not exist. So now we have 50 volt being opposed by 6 and 2 in parallel and then in series with 3. Okay, so please realize the structure first, and then let's try to find out what is the current that is now emerging from 50 volt. Okay, 6 and 2 in parallel means 3 times 2 is 6, so 2 into 3 by 4. Okay, or in other words, that's 2 into 3 by 4 is equal to 1.5. Okay, so this 1.5 and 3, because they are in series, together constitute 4.5 ohms. So 50 divided by 4.5 is the voltage, is the current that emerges, okay, as the new current, okay, by virtue of short circuit, and then it divides into two. The one that flows through the 2 ohm resistor ends up in the short circuit. So that's equal to two contributions, 0.5 Vx from the current source, and then again we have 25 by 3, that is 50 divided by 4.5 into 6 by 8. That gives us the next contribution from the 50 volt source, which is 25 by 3. Okay, so now we have IN as also Vth Okay, we can take the ratio of the two, okay, and you can see that, okay, IN is, yeah. So, meanwhile, we can also solve for Vx in this problem, that is in this context, when we are trying to find out the Norton's current, where Vx is the voltage across the 6 ohm resistor, or it's the voltage across the 6 ohm and 2 ohm resistors in parallel, because of the short circuit that we have created for calculating the Norton's current. Okay, so when 6 and 2 are in parallel as before, that's 1.5 ohms, and then we have 3 ohms. Okay, and this 50 volt now gets divided between the potential divider of 3 and 1.5 ohms. So that's equal to 50 into 1.5 divided by 4.5. That gives us 50 by 3 as Vx. Okay, now substituting 50 by 3 in IN is equal to 0.5 Vx plus 25 by 3 tells us that IN is equal to 50 by 3. Okay, so we have calculated them completely separately. This is going to be the difference with respect to the previous problems that we have been handling. Okay, so now it is as simple as that is RTH or ZTH is as simple as VTH, which is equal to 100 by 5 divided by IN, which is equal to 50 by 3, and so we get RTH as a nice value of equal to 1 ohm. Okay. So that's it. So now we move on to the next problem. Yeah, we move on to the next problem. That is problem number 3. Okay, again a little bit of calculation is there, though it looks a little different from the previous problems. I hope you realize that. Okay, and we also see that we have a 0.4 I1 as the dependent current in the whole context, and we also see that I1 is the current that is now flowing through the 20 ohm resistor. Okay, and we are supposed to find out the voltage V, which is marked across 30 ohms. So this is the major difference. We have to find out the voltage across the 30 ohm resistor as V. Okay, as mentioned as V. Okay, so now what do we start off from? We start, of course, because there are too many current sources, including the 4 ampere source at the left end and the 0.4 I1 on the right end. We can try to have an understanding about the current pattern. Okay, so when 4 amps comes and 4 amps comes to the junction above the 20 ohm resistor, I1 moves downward. So what seems to flow through the 10 ohm resistor is now 4 minus I1. Okay, so that's one part of the bargain. But now moving to the other side, we also see that we are having a current flow through 30 ohm resistor, which is caused by and it creates a voltage by multiplying that current by 30. Okay, so now we can now write out the current that is flowing through the current that is flowing into the 30 ohm resistor as in terms of what we are supposed to find out, which is V, which is so as V by 30. Okay, so now V by 30. Okay, so now let's come to the bottom part of the entire circuit, where all the 4 branches are now converging, okay, in terms of currents. So now we are having V by 30 from the 30 ohm resistor flowing downward. We also have I1 flowing downward, and then we have 2 current sources where currents flow upward. So V by 30 plus I1 is equal to 0.4 I1, that is a dependent source, okay, plus 4. Okay, so now we can set V to one side and place the other things all on the other side. So we see that, so now 0.4 I1 minus I1, okay, that's equal to 0.6 I1, okay, and then we also have minus plus 4, okay, on the right hand side, and then multiply everything by 30. So we see that V, which we are supposed to find out, is equal to minus 18 I1 plus 120. Okay, so that's one part of it. Okay, so now we have a relation between V and I1. Okay, so now let's find out whether voltages can help us, because there is what is called as a voltage source 60 volt. Okay, so we are using the 60 volt source as also all the current distribution that we have calculated so far, to find out whether we can solve for at least one of them. Okay, so now what is 60 volt? Okay, 60 volt is a voltage, okay, which is negative at the left end and positive at the right end. Okay, so now let's balance all the other voltages such that it starts from negative, okay, and when you look into the loop, it starts from negative, goes on to positive, okay, and if and this is what we call as a potential rise. On the other hand, if terminal at which we arrive at happens to be positive, then it's going to be a voltage drop. As in this case, we see that 10 ohms into 4 minus I1 when we are balancing with 60 volt is positive. Okay, so it is 10 into 4 minus I1. Okay, but now we arrive at 20 I1, which is now, because of the current flow downward, which is now a drop. So it is equal to minus 20 I1. Okay, and then we again have a rise in 20 or in 30 ohms as given by V. Okay, I suppose this equation is also very clear. That is 60. So this is how we have to proceed. That is where the voltage is given or the voltage source is given. There you'll go for the voltage distribution. In all other aspects, you'll be talking about current. Okay, so now that's the reason why this question gives you a better understanding. So now we see that 60 is equal to 10 into 4 minus I1 minus 20 I1 plus V. Okay, so again redistributing, we see that we have, and also realizing that we are having, we have a value for V as equal to minus 18 I1 plus 120. We put them all together, okay, such that we have only I1 to solve, and so I1 becomes the same as equal to 100 by 48. I suppose meanwhile we have also seen that 20 is equal to 120 minus 48 I1 is how we reorganize this equation. Okay, so now we see that I1 is equal to 25 by 12. So substituting that in V is equal to minus 18 I1 plus 120, we see that V is equal to 82.5. Okay, so meanwhile you can also solve between two equations, okay, simultaneous equations, if that is easier done for you. I have always used substitution because that appears easier to me. Okay, so both methods are there, but then writing out the equations, okay, of course you will have to use your paper, the additional paper supplied here, because it is a little bit too much of calculation in the mind. Otherwise you can use only your mind. Okay, so but of course the mind has to be very much strong and working to see that to draw out useful information. Okay, so let's go for the next problem. What do we see there? That is, it's the fourth problem, and we have a centrally located dependent source. It's a current source 0.04 Vx, and Vx is the voltage across the 5 ohm resistor. Okay, so now, okay, immediately when you see Vx, remember that the current is already available there because the voltage is Vx. So Vx by 5 is the current that flows through both the 3 ohms and 5 ohms. Okay, so these are the realizations that come when we go from the dependent source to the location where it is dependent on. Okay, then we have what is called as a 60 volt source. That's another of the sources, but it is independent. Okay, we also have 5 ohm and the earlier mentioned 3 ohms and 5 ohms. Okay, so this is the general layout of the circuit, and what we are required to find out is from the circuit shown in the figure, the magnitude of the current in amperes through R2. So we know that the current through R2 happens to be the same as the current through 5 ohm. Okay, and that's equal to Vx by 5. Okay, so we need to find out I is equal to Vx by 5. Okay, so Vx is what we are trying to find out. Okay, so now we have a 60 volt source at the other end, and we also see that 0.04 Ix arrives at the center junction, and Vx by 5 flows out into the Vx by 5, which is equal to 0.2 Vx, flows out into the 3 plus 5 ohm series there, which means that 0.2 has to be created by another set of current flowing from the 60 volt source, which is equal to 0.16, because 0.16 plus 0.04 Vx gives you 0.2 Vx. Okay, so now 0.16 Vx, that is current distribution is appropriately clear. That is 0.16 Vx comes to the junction. It is joined by 0.04 Vx from the current source, and together they flow as Vx by 5 or 0.2 Vx. Okay, in the 3 ohm 5 ohm series. Okay, now going on to the voltage balancing, 60 is equal to, okay, the full peripheral circuit where we are having 0.16 Vx into 5. Okay, which is equal to 0. Okay, so that's 0.8 Vx, and then we are having Vx by 5 into 8, okay, which is equal to 1.6. Okay, so Vx 1.6 Vx. Okay, Vx is taken out, so 1.6 plus 0.8, that gives you and then Vx is equal to 25 divided by 2.4. Okay, so that gives you Vx is equal to 25. Okay, and the current through the resistor R2 is Vx by 5. So 25 by 5 is equal to 5 ampere. Okay, it's not a very tough problem, but then your mind should be properly tuned to start off from there, to know where to start off from. Okay, now this is actually a very simple problem, though there are two dependent sources, and it would merit you 2 marks in GATE. Okay, 2 marks in GATE is the difference between qualification and non-qualification, or also the top ranker and the next ranker. So definitely be sure to do the dependent source problems, because they give you more marks, and it's almost a sure question in the GATE contest. Okay, so I'm talking mostly to students who might do the GATE examination. Okay, so what do we have here? Two dependent sources. The first one is a voltage source, okay, with 0.5 V1, and where is V1? V1 is the voltage across 8 ohms, okay. And then we also have a current source, okay, which is I, and this I is flowing into the 8 ohm resistor and going back because of the short circuit. So now already something is solved, that is I is equal to V1 by 8. Okay, I suppose this is the way that you can solve. This is the way that you can try to make the most of the dependent sources. Okay, so I is the current that has to flow, and it has to come back, and it will flow through the short circuit between that is already existing there, and so we see that I is equal to V1 by 8 kilo ohms. Okay, so it's all in milliamps. Okay. And now what is, okay, so and where is this I? I is coming from the 75 volt source and flowing through the 2 kilo ohm. Okay, so that's I is given in milliamps. So we will be doing everything in milliamps. Okay, because it's all kilo ohms. Okay, all the resistors are kilo ohms. Okay, so the 75 volt independent source has also 2 kilo ohms and 8 kilo ohms. Okay, so this is the general structure, the short circuit at the center. Okay. So now let's see what is required in the circuit below. The magnitude of the voltage V1 in volts across the 8 kilo ohms resistor is what? Okay, so what do we do? So as I said before, we already have I is equal to V1 by 8, and now we can balance out the voltages in the left loop. Okay, because the left loop is independent of the right loop, because there is a short circuit, or in other words, for balancing it's easier. Okay, so what is 75 volt? Okay, so 75 volt is the same as equal to, if you look from the other side, we have 2 kilo ohms multiplied by I, so I'm writing it as 2I because kilo and milli cancel. Okay, and we also have 0.5 V1. Okay, so there are two voltages balancing the 75 volt source. One is 0.5 V1, the other is 2 into I. Okay, so now we know I is equal to V1 by 8. So there are two, so the whole equation is in V1. Okay, simply, so V1 by 8 means V1 by 2 into V1 by 8 is I. So 2I is equal to 2 V1 by 8, or 0.25 V1. Okay, so 0.25 plus 0.75. 0.5 is equal to 0.75 V1. So V1 is easily calculated as 100 volts. Okay, so this is a very simple problem, but it would have given you just, you need just your mind and no paper for solving it. Unlike in this problem, here there's a little complication. This is the toughest problem that I'm offering in dependent sources, and with this we come to an end. Okay, we don't use the superposition theorem as written here. This used to be a 5-mark problem, but we are not, okay, we are doing it our way such that the understanding is completely established. Okay, so what do we have here? We have the dependent source 2.5 VB. Okay, so it's VB. Okay, it's VB, and it's also a voltage source. Okay, so where is VB? VB is the voltage across the 1 kilo ohm resistor. Okay, and we have 2 kilo ohms and 4 kilo ohms, and we also have more voltages. Okay, so we have what is called as 90 volt on one side and 40 volt on one side. Okay, so now we have all voltages. Okay, and we are expected to find the current I. Okay, using the superposition theorem, which we discussed, we are trying to find out the current I. Okay, using the Kirchhoff's laws only. Okay, so what do we do now here? Okay, because there is no current to distribute, we start off with the voltages. Okay, the voltage is very simple because VB is given as the voltage across the 1 kilo ohm resistor. So if you look at the complete outer loop, okay, so we can start from 90, no, we can start from 40, so 40 volt, and then there is another voltage rise 50, that is VB, which is equal to 40 plus VB now, and then there's a drop 90. Okay, so that's minus 90, and that will give you the voltage across the 2 kilo ohm. Okay, on the other hand, if you look at it from the other side, from the in the opposite direction, then 50 minus VB, okay, that is 90 minus VB minus 40 is going to give you the voltage across the 2 kilo ohm resistor. Okay, and that is and the direction is shown in this way. Okay, so this is another way that you can do the problem. So 50 minus VB is the voltage across the 2 kilo ohm resistor. So that's resolved. Okay, now we have only two different resistors across which the voltage need to be found out, just like the different elements in the circuit wherein the current distribution was found out. Okay, so what is the voltage across the 2 kilo ohm resistor? Okay, so there's 90 on one side and 2.5 VB on the other side. So we have to find out the difference between them, and that is going to be the voltage across the 2 kilo ohm. So 90 minus 2.5 VB gives you the voltage across the 2 kilo ohm resistor. What about 4 kilo ohm resistor? Similarly, you can use the two voltages. Okay, so or you can use you can also use the voltage, and that is the difference between the 90 that is the difference between VB and 90 minus 2.5 VB. So it's the same as equal to minus 90 plus 3.5 VB. With all directions as shown, the directions have been intentionally placed here. So you can also use another method. You can also say that 50 minus, because either way you work out, it will be the same as equal to minus 90 plus 3.5 VB, so long as the direction is as like this. If the direction is reversed, then it becomes 90 minus 3.5 VB. That's all. Okay. So now all the voltages have been all the voltages across every element is known. Okay. Now we have known in terms of VB. So now let's go for go to find out I. For that, okay, of course the current distribution is important. Okay, so let's go for the current that is flowing into the junction at B. Okay, the junction is at the far right. Okay, so that's given by 50 minus VB by 2. Okay, because that's a resistor. There's a resistor and the voltage across it is 50 minus VB. So the current flowing into the junction is equal to 50 minus VB by 2. Okay, and now we also have another current flow there, which is given by minus 90 plus 3.5 VB, which is the voltage across 4 kilo ohms divided by 4. Okay, and now that is going to be the current that is flowing into the 1 kilo ohm resistor, and that's given by the current there is given by VB by 1. Okay, so this is one equation that we have, again connecting between VB and I. Okay, this is exactly what we are doing. Okay, so now just rearranging, we see that 47.5 is equal to 2.375 VB. Okay, so that's one part. Okay, and now we go for so that's one part, and now we go for another. Okay, now we need to find out what is the current I. Okay, so what's the current I? That's equal to 90 minus 2.5 VB by 2. Okay, from which we subtract out 90 plus 3.5 VB by 4. Okay, and we get, okay, so meanwhile we have to find out VB. So how do you do that? Because 47.5 equal to 2.375 VB has already been derived, we can find out VB is equal to 20. Okay, so we can substitute for 20 in 90 minus 2.5 VB. We see that it's equal to 40 volt. Okay, and when we substitute for VB in minus 90 plus 3.5 VB, we see that's equal to minus 20. So 40 by so I is now I, which we are supposed to find out, is as simple as 40 by 2 minus 20 by 4. Okay, and that gives you the current I as equal to 25 amps. Okay, very it looks a little complex, but then if the pattern is very clear to you, that is, you distribute either current or voltage. Okay, and then you pick up the voltage. Mostly you pick up the voltages later on to have what is called as the balancing, and then solve for things. See here, what we have done is we have distributed the voltages, and based on the voltages across the resistors, we have found out the currents, and then we have balanced the currents. Like in the earlier case, we did what is called as 50 minus VB by 2. Okay, and that is one current that is arriving at junction B, divided okay, and then it is added to by minus 90 plus 3.5 VB by 4. Okay, and then together this current flows into VB as equal to, okay, VB by, okay, into 1 kilo ohm as VB by 1. Okay, as simple as that. And then you just, so everything is in VB, so you can solve for VB is equal to 20 volts, and then 20 volts can be 20 can be substituted in 90 minus 2.0 VB as also 90 plus 3.5 VB. Okay, and then divide by the resistors to get the different currents, and then whatever current leaks out into 2.5 VB you can calculate. Okay, so this is actually very simple. Let me hope that you have understood it properly, and you will be able to do any problem in differences. Okay, next we go for to AC networks. Okay, thank you.